is at least I will outline the problem here. Whitening filter, and it's also kind of very closely related to a problem called spectral factorization. Okay. So let me explain to you both. So if you have a system h of t with transfer function h of omega, we saw that so if this is white noise, first of all, the output is the input process convolved with the system impulse response, right? This being an LTI system. And if this is white noise, for example, the output noise, output process power spectrum is the input power spectrum multiplied by the system transfer function squared, but because this the input noise is white, we can write it like this, right? Because S omega is 1. So if you look at this power spectrum, see, it's always appearing as a square of a system, and that is what we mean by spectral factorization. So the problem is, given a spectrum, can you find the system behind it? So the interpretation is the following. I have a spectrum. So the spectrum, of course, is going to be a Fourier transform of some autocorrelation function of it, right? That we studied. And this is non-negative. So I can compute the spectrum. Now, if I can imagine in my head that the spectrum is given being generate, or the system, the process is being generated by a system being driven by white noise, look at this. Then of course and if the white noise spectral density is 1, then this power spectrum can be written like this, where h omega is the system transfer function. So the problem is finding the system from the power spectrum. That's what we mean by factorization. But it is not that simple because it is frequency, etc. is involved, right? But so let me do this in the continuous case, then we can also do this in the discrete case, and I'll do this in the rational case and show you how to and then we will discuss the inverse problem, whitening problem. And the whitening problem is the other way. In other words, is it possible to, so given a system, given a process, is it possible to find a linear time invariant system where the output will look like white noise? Is it possible to find a this is white noise. So, but I think you should be able to see that if I can find this system, look here, suppose I can find this h of s, right? So this also can be written as h of s multiplied by h of minus s, s equal to j omega, right? Because s equal to j omega is h j omega. S equal to, when you put minus here, h of minus j omega. So this is the same as h multiplied by h star for real systems. So what we are asking is, given a power spectrum, can I write it as h star? Now, because we are dealing with systems which we may want to use it, you can impose the condition that this is where, as electrical engineers, you may want to say that I want the system also to be stable so that it will be useful for me to do some simulations and so on. So now you can expand the question again. If I give you a power spectrum, so generally whatever, I draw a power spectrum. Okay. Is it possible to find a system whose transfer function is exactly matches this? These are the type of questions we ask in spectral factorization. But we don't want any system, we also want the system to be stable. You can put one more condition, you may or may not, you also, if you flip the system, in other words, the inverse of the system also should be stable. So you may say that is very strange, why do you want the inverse? So first of all, let's look at this. Suppose the system is like this. So what do we mean by, if I flip it, this will generate the poles, right? This, of course, if you like this, S minus Sk is a pole, right? And if I write this as factors, this is S minus phi, then phi is a 0, right? So what, if you want the system to be stable, anybody remembers what are the conditions on poles and zeros?
The poles must be in the left side.
All right, so that's good. If it is if you are doing this in the discrete domain, the poles must be within the unit circle, right, etc. So let's just do the so that's the condition, right? Because if a pole is here, let's say a pole is at minus a, so the system is going to look like what? If a pole, that's a pole, right? S minus, so the pole is at S1. S1 happens to be minus a, so the system is a transfer function is S plus a. What is its inverse transform? Anybody? You forgot? E raised to? Yeah, minus at ut. See, that goes like this, right? So this is a decaying system, stable system. If the pole was on the other side, this will be exploding. That will be an unstable system. So that's the simple argument. So you want all the system poles to be on this side, right? And moreover, if the system is real, you know the poles are going to occur in complex conjugate pairs, right? You know that much. Same thing with the zeros. Zeros going to occur in complex conjugate pairs. But as you know, the zeros are not, for stability, the zeros can be anywhere, right? But if I insert this condition, then what happens? I am insisting that not only the system be stable, if you flip the system, I want that to be also stable. That means then what are the conditions I am putting on the zeros? Anybody?
They will become pole and
the zeros are, because if I flip it 1 over h, if I flip it 1 over h means B will come here, A will go here. So this will become the poles of the inverse system. I want those poles also to be on the left half side. So translating this for rational systems, what we are saying is, given a spectrum, is it possible to find the find a factor h such that these conditions are satisfied? So if you can call it, if these conditions are satisfied, we'll call this the Wiener factor, same Wiener. So let's look at some examples. Okay, I'll do a few examples. So first of all, look here. If I replace S by j omega, what happens to omega squared? Or if I square it, what do you get? S squared equals? Minus omega squared. Or so if I think we already learned this, right? If the process is real, the spectrum is even, right? Yes? Why? You already forgot the argument? Because R of tau is R star of minus tau. The process is real, so R of tau is R of minus tau, right? So the power spectrum has this even property, right? For real processes, this is true. Then look, now listen to the argument. If this is also a ratio of two polynomials, do you see that only omega squared terms can be here? You see it? Otherwise this cannot be satisfied. So the first observation is the power spectrum has to be, if it is in terms of a rational function for even for real processes, the power spectrum has to be functions of omega squared and higher powers only. So all these are power spectrum, right? Is this a power spectrum? This is a function of omega squared. Is this a power spectrum? What is the property on power spectrum? Simple property.
Always positive.
So what here, this is not always positive because for omega greater than, so that's why I made this to be. How about this? Is this a power spectrum? So you see, you get simple conditions. If it is a power spectrum, first of all, it has to be positive. So any function, any omega is going to appear as omega squared or higher powers of omega squared. And so consequently, if I am replacing, look at here, if I am replacing on h by j omega by s, I should replace omega squared by what? Huh? Look at here, omega squared is minus s squared. So this is what I should be replacing. So I'm going to rewrite this as 1 over 1 minus s squared. The question is, I'm asking is, can it be written like this? That's the question here. That's what I mean by spectral factorization, right? And I want, remember, so many things going on. I also want these two conditions to be satisfied. So let's look at the location of the poles and zeros. There are no zeros. Where are the poles? Where are the poles? You don't know how to factor this, no?
1 minus s, 1 plus.
So one pole here, right? At minus 1 plus 1. So then the answer is obvious, right? If I put one pole, this I want to be stable, and the other one is going to be, I can associate like this, right? Right?
Yes.
So the problem solved. I hope you saw it when the punchline came and went. So the spectral factor is this. Now look at this. This is stable by design. So if I had put here, that's also fine. This is a spectral factor, except that this is unstable, you see, right? So if you want, because of this stability condition, I am going to, so we'll do simple thing first. I mean, then I'll come to that omega 4, right? So this is not stable, so I'm going to put the stable factor here, and then multiply, I get this back. So this is the filter I've been looking for. This is stable. Its inverse is, of course, it's a polynomial, so it's always stable, so I don't have to worry in this case. So let's look at the second one if you are happy with this. So first of all, we will rewrite it in s. So omega squared is replaced by, so 1 minus s squared. Omega squared is, so where are the poles, where are the zeros? There is one set of zeros here, right? Where are they?
Minus 1 and plus.
All right, so minus 1 plus 1. And where are the poles? Huh? All right, so a pole at minus square root of 2 and a pole of plus square root of 2. So remember, I want to write this like this. So you can say whatever you do here, you have to give an equal, one term here, one term there, right? So what would you do? The answer is obvious, right? So remember, so of course the pole, because you want the system to be stable, this should be s plus square root of 2. But because you want the inverse to be stable, you have two choice. I can put s minus 1 here. But then this, when you flip it, it's going to be an unstable system, right? So s plus 1 is the correct answer here. And this will be what? 1 minus s and square root of 2 minus s, or the other way. Right? So look at this system. It is stable because the pole is at the left side. It is, if you flip the system, the pole is s equal to minus 1, so that's also stable. So both these conditions are satisfied. Now, I haven't quite explained to you why we need the second condition. We'll see that. But let me just, since you mentioned, let's just, so first procedure is to replace, if you want to find the spectral factor, replace omega squared minus omega squared by s squared. So where are the poles? Anybody? S equal to, look at here, s squared equal to minus 1. Where are they? Huh? So there is one pole here. No, I'm sorry, 0. But you see, what is its order? So there are two of them, right? At j. And similarly here, minus j. 0, these are zeros, two zeros, right? And look at the poles. Where are the poles? S equal to square root of 2 multiplied by j, but there are how many, so there is a pole here, there is a pole here, but what is the order of each pole? 4, so there is 4 of them here, right? J square root of 2 minus, so j square root of 2, but again 4 times, right, at the same place. Now let's see how to write this, satisfying all those conditions. If you do something here, you have to do something here. So let's look at each term. This is what? This is of the form s plus j, right? If I put it here, I have an option to put it here also, right? So these two taken care of, right? Yes? This was plus j, so this should be. These are zeros. There are 2 zeros here, right? So I can put 1 here and I guess 1 here, right? As I said, that you don't have any choice, because whatever you do here, the minus 1 you have to put it at the other side. And same thing with poles quickly. So you have s plus j square root of 2 here, but then you can put the s of hold on. Anything? Did we take care of everything? We only took care of one set, right? Look, how many zeros are here? Anyone? 1?
4, 2 plus 3 is 2 minus 1.
All right, so in this case, it's going to be, so I took care of all the terms, right? One term here, one term here. 1, 2, 3, 4, all the 4 terms are here. This together, if you want, you can read it as what? S squared plus 1, right? This is also S squared plus 1, which is fine, because when you put S equal to minus S, it satisfies. Similarly here, S plus J2, S minus J2, same thing here. So together, if you want, you can read it as S squared plus 2 multiplied by, there are 4 of them, so I'm going to put a 2 here, 2 here, 2 here, 2 here, just to take care of them. So you may say, let's see, all the conditions are satisfied. This equation is satisfied. These systems are called marginally stable because the pole is on the j omega axis. And if you flip it also, it is still marginally stable. At least certainly it is not unstable, right? So this is the best you can do here. So this will be the spectral factor corresponding to the Wiener factor will be just this. All right, let me take the, one more case, the last interesting case. So I'm just going to write it here and then. That's fine. So how will this power spectrum look like? What is the value at omega equal to 0?
1.
And what is the value at omega equal to infinity? So it's certainly it's going to look like this. So it's sort of a, this is the power spectrum, right? It's a low pass filter, right?
Yes.
I mean, with a slightly different shape. This also is low pass, right? So this is your SXX omega. The first step is I want to write this as h of s multiplied by h of minus s. So where s is j omega, which is the same as saying that omega squared is minus s squared. So first step is to rewrite omega squared by minus s squared. So this is 1 minus s squared. This is 1 plus s4, right? Minus s squared. And the numerator factor is easy because this is s plus 1, this is s minus 1. So we know that this belongs to here, this belongs to here, right? So the other one is a little tricky, so I'm just going to, so this equation has how many poles? Where are they? You don't see them? So you have to solve which is s4 plus 1 equal to 0, right? That's the same as s4 equal to minus 1.
Yes.
Well, minus 1 is e raised to j 2k plus 1 pi, right? Because e raised to j pi is minus 1. So put k equal to 0, 1, 2, 3. These are the, there are 4 poles, right?
Yes.
So all the roots are, so they are the 4th roots of unity, which are this, right? Okay. So the SKs are e raised to j 2k plus 1 pi by 4. So where are they? Anybody? You forgot all this stuff? Where is the first pole? Put k equal to 0. You don't have to do any guess. So where is it? So one pole is here, right? Pi by 4. The next one here, k equal to 2. K equal to 2, k equal to 1. That will be 3 pi by 4 here. The other one here. The other one here. So I'm going to call it S1, S2, S3, S4. Look at here. If this is S1, this is its complex conjugate transpose, right? If this is S1, you can see this is minus S1, isn't it? Because you change the real part and imaginary, real part is positive, imaginary part is positive. You make it minus, real is negative, imaginary, so that's this point. This is its complex conjugate, so this is minus S1 star if you want. But you can see these 2 poles are on the left side, these 2 poles are on the right side. So we should associate this where? With this or with this? Yeah, because you want it to be stable, right? So now we can mentally write it up. H of s, the numerator is s plus 1. The denominator is, you see it, if I just call it S1, it is pretty clear this is S1 star, right? Remember, this is no high school algebra. And what is its minus? So this is plus, this is plus. So if I make it minus, 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 so this must be minus S1. And its complex conjugate is this. So you want S minus, S plus S1, S plus S1 star. That's because the root is S minus of the, so where is the root? A root is at S equal to S minus S1, which is here. S equal to minus S1 star. So these 2 we want to associate with this. But see, this now becomes, the denominator becomes S squared plus 2 real part of S1 multiplied by S plus S1 squared, right? What is the real part of S1? First of all, S1 is e raised to j, remember k equal to 0, not S1 actually, it should be S0. It doesn't matter, but it's, so you put k equal to 0. So k equal to 0, this will be k equal to 0. Pi, so this is cos pi by 4, right? E raised to j pi by 4. Its real part is cos pi by 4, which is how much? 1 by 2?
Under root.
Oh, square root of 2. So this part is cos 45 degrees, which is 1 over square root of 2. So this polynomial comes a squared plus square root of 2 plus what is the absolute value squared? Hello? Absolute value squared is what? Absolute value of this. So that's 1, right? So that's the denominator. This is a Butterworth filter, whether you know it or not, right? At least the denominator. This is stable. Why is it stable? Why is this filter stable?
The poles are
Where are the poles of this? We just found out, look here, right? The poles are here and here, so that's stable. If you flip it, what happens? Where is the pole? If you flip this system.
S equal minus 1.
So that's also, so you see, this condition is satisfied, this condition is satisfied. And h of minus s is whatever it is. So h of minus s is, of course, minus s plus 1 over s squared minus square root of 2s plus 1. Now you can clearly see that if you look at the zeros, it will be s equal to plus 1, and the two poles of this are this, so everything matches, fits. This is what is spectral factorization problem. Given a spectrum, give me a system which is stable and its inverse is also stable. This is a rational case. You can do it in the discrete domain also, but more challenging will be if I just draw a line for whatever reason. This looks like a good spectrum. Question is, give me a system, a best system which will approximate this spectrum as closely as possible. So this is the topic of my system identification book. If you ever get to teach here, let's see, given a system, how to find I'm given a spectrum. So you can say this is the spectrum of wind, sea wind, for example, or hurricane a certain month. If you plot the power versus frequency or some parameter, this is the power distribution. Give me a system representation of this process. Then the idea is that you can think of whatever is the phenomenon you are dealing with, a white noise is driving this system to generate this peculiar power spectrum. So let me finally connect it with this match filter problem. Or let's just connect it with this this problem now. So now this must be easy. So look at here. I have a system. So we just went through this problem of finding I'm given a spectrum. We just went through this problem of finding a system whose system transfer function squared is equal to the power spectrum. Okay, this is done. That's what we have done. This is spectral factorization. So let's see how to address. Then let's look at this problem. Here I want SWW omega to be 1. That's not what I mean by white noise. I want to whiten so that the output looks like white noise. But what is the relation between output and the input power spectrum? Anyone? So output power spectrum is?
Input in spectrum multiplied by
All right, what is input spectrum?
Yes, yes, yes.
Omega multiplied by?
G of omega.
Yeah, G S equal to J omega. So this is the relation, right? But look here, this is 1. And we also know that we just went through this. This is equal to, so of course I can write one more line. This is equal to, if you know how to do the spectral factorization, given the spectrum, I can write this as Hj omega squared, right? Multiplied by Gj omega squared. So I am looking for G of S, so at least I see symbolically Gj omega squared is 1 over Hj omega squared. And if I replace J omega both the places, I have two solutions. Certainly I get G of S is equal to 1 over Hs. But you see, if HS inverse of HF is stable, we can make sure this system is stable. So if we have later, we want to do spectral factorization, I'm sorry, the whitening filter, then we want this to be a stable filter. That means this should be stable. 1 over H should be stable. But this is coming from here. So not only H should be stable, we want also this peculiar thing of 1 over H being stable. So that's where the Wiener factor helps, because Wiener factor we can make is designed such that by construction both the filter and its inverse are, and I just went through a few examples, right? So finally, if you have a signal is coming in colored noise n of t, whose coloring is like this. So we just went through this. This can be written as this is the power spectrum of the noise, so that's low pass, right? That's low pass. But it has a system representation, low pass system representation. So we want to pass this first of all, and as I said, what we have learned is to design the match filter for white noise. So I am first going to convert this into by a whitening filter. So what will be the whitening filter here? To convert this noise into white noise, that's my, this is colored noise. I want to convert it into white noise. So look here, this spectrum has this factorization. So that's this factor, H of S. So whitening filter will be what? Its inverse. So in this case, it's going to be 1 plus S. That's a differentiator, right? A constant plus differentiator. So you don't have to worry about, it's already stable. So in any case, the G of S would be 1 plus S, okay, symbolically at least, right? So whitening filter G of S. So, but the trouble is, in this process, the S will become something else. What did we write? Let's say SG of T, a new signal, because this will be ST, look at here. Whatever is the transform of this gets added by S multiplied by S corresponds to, as you know, differentiation, right, in time domain. So then of course you know that the right filter to use here will be what? Which will be what? Match to what? Match to whatever you see here. Solve only the immediate problem, right? So this will be SG of T naught minus T. If it is complex, it is this. But the whole problem is solved by the cascade of two filters, whitening and matching, right?
Yes.
So this problem might make more sense if you say that my original spectrum was a high pass, let's say if it was like that. Then of course I could write this as, so this is my H of S, right? So my G of S would be 1 over H of S, which would be 1 over S plus square root of 2, whose inverse transform is e raised to minus 2t ut, right? So your Sg of t would be S of t, whatever is the input pulse, need to be convolved with e raised to minus square root of t ut. Right? So if this happens to be a pulse like this, you just convolve it and see what it is. And then that needs to be flipped, and shifted and so on, right?